All right, so this video is going to start the work and energy packet. We're going to go over the pages 2 through 5 in this video. So do you know the meaning of work? The everyday meaning of work is different from the science definition of work. So we don't mean like putting in work from studying for a test. What we mean is actual physical, mechanical work where there's a change or transfer of energy. Okay, so mechanical work or transfer of energy occurs when a force is applied through a displacement or distance. Okay, so that basically means work equals force times distance or displacement. So W would be your work, F would be your force, and then D would be your displacement. Remember, displacement just means where did you end up versus where did you start. Okay, so it's basically the distance between your starting point and your ending point. Okay, so your units for distance or displacement is going to be meters. Okay, so make sure you're in meters. Units for force, okay, is going to be newtons. Okay, and the units for work is actually called joules. And that would just be a capital J for that. Okay, so again, I know we just did impulse equals force times time, J equals F times T. But this is, we're talking about a unit here, not an actual abbreviation for something. Okay, like in an equation. We're just talking about simply units here, but if that confuses you, you can always use this one. You can say Newton meter. Because if work equals force times distance, and force is newtons and distance is meters, newtons times meters is the same thing. So it's honestly up to you, whichever one you prefer. So work can be positive or negative depending on the direction of the force. That means you can have positive and negative work. Okay, usually your negative work is going to be something like friction, kind of working against you. Okay, positive work would be going with the flow of the motion. So we're going to start off with some basic examples. So a person is pushing a lawnmower with a force of 45 newtons. So there's your force over a distance of 30 meters. Okay, how much work is being done? So you're looking for work. Work equals force times distance, so 45 times 30. And you're going to get 1,350 joules. Okay, the car is exerting 355 joules of work, so I actually gave you work now, over a distance of 15 meters. Calculate the force of the car, so you're looking for F now. So 355 equals your force, which we don't know, times 15. So I would divide both sides by 15, and I'm going to get a force of 23.67 newtons. Next one is a 65 Newton object is being lifted. Okay, so this is actually a force, and weight is actually a force. And we'll talk about that more here in just a second. But when it says a 65 Newton object is being lifted, that's technically the weight of an object. So weight is a force. So it's being lifted, which results in 550 joules of work. So there's your work. How high is the object lifted? So that means you're looking for distance. Okay, so work is 550 equals force, which is 65. Times distance. Okay, so divide both sides by 65, and you're going to get a height of 8.46 meters. Okay, so those were just basic, okay, work equals force times distance, so nothing too crazy there. So we're going to kind of start tacking on a little bit here. So remember, our whole goal of work is work equals force times distance. If we have force and distance, then awesome. All you got to do is plug in, then there you go. If you don't have one of those, then we got to find it. Okay, so this problem here, so we're bringing back Daffy T. Okay, so don't get too hung up on that. A force of 25 newtons, so I gave you a force, accelerates a cart across a frictionless surface from rest, so VI would be 0, to a velocity of 8 meters per second, there's your VF, in a time of 2.5 seconds, there's time. How much work is done? You are looking for work in this case. So remember, you need force and you need distance. Do I have force? Yep. Do I have distance? I do not. But I actually have quite a bit here that could help me. I've got VI, VF, time. So what we can do is remember D is a part, or distance is a part of Daffy T. Okay, so VI is going to be 0. VF is going to be 8. Time is 2.5. Okay, distance is what we're looking for. That means we do not care about acceleration. So remember, we're going to use the equation that we do not care about. So we're going to use equation number 2. Okay, you do not want to use the one with the question mark. Let's just say you did. Let's just say, well, I'm going to use equation number 1 up here. If you look in that equation, distance isn't even in it. So you'd already be at a dead end before you even started. Okay, so we're going to use equation number 2. So D equals VI plus VF, so 0 plus 8 over 2 times your time, which is 2.5. Okay, so 8 divided by 2 gives me 4. Multiply that by 2.5, and you get 10 meters. So that is actually how far it went. So there's your distance. So now, do I have force? Yep. Do I have distance? Yep. So now I can do work equals force times distance. So 25 times 10, and you're going to get 250 joules. So there's your answer for that. So all we did was we used Daffy T to help find that distance. Now we're going to talk about, this is where I'm talking about bringing back that kind of weight thing. It says a student lifts a box of books that has a mass of 15 kilograms, so that's a mass, up 0.8 meters. There's your distance. How much work does the student do? So work equals force times distance. Do I have force? Nope. Do I have distance? Yep. So I need to figure out what my force is. So remember we said weight is a force. And how you find weight, okay, so mass and weight are different. So we got to remember, we got to go back to kind of basic science there is no matter where you are, your mass will be the same. Okay, but if I asked you what was your weight on Earth versus the moon, it'd be different, right? Because your instinct would go to, well, there's less gravity on the moon, so therefore you weigh less. So that's the thing here. Okay, if you want to find the weight force, it's mass times gravity. So what we're going to do is we're going to take that mass, okay, of 15, gravity in this case. So usually what I see is I see some confusion here. I'm like, well, why don't you use yet negative 9.8? Is we're talking about a student who's lifting the book. Okay, we're lifting this box of books. So they're lifting it up. Okay, so the student's doing the work. Gravity's not doing the work. Okay, so we're going to keep that a positive 9.8 since the student's doing the lifting. Now, honestly, would it affect your numerical answer? Not really. Okay, but gravity is not the one doing work here. Okay, so if gravity was doing the work, like if this book was falling, then yeah, we would do negative 9.8. Okay, but we're going to do 15 times 9.8, and that gives you 147 newtons. So there's your force. So work equals force times distance, so 147 times distance, which is 0.8, and you get 117.6 joules. Okay, so again, if we made that a negative 9.8, that would make my work or my weight negative, and which would make my work negative. So remember, a negative work means it's either falling or going against you. In this case, we're just talking about how much work was done by the boy or student lifting the books. Okay, so that's why we kept that 9.8 positive. Now what we're going to do is how much work is done on an 8 kilogram wagon. So we're looking for work. I have an 8 kilogram wagon. So you got a mass along a flat sidewalk with a force of 60 newtons opposites to its direction. So your force is actually going to be negative 60 newtons. So make sure you pay attention to direction. Brings it to rest. So VF would be 0. And then in 2 seconds. So there's your time. Okay. So do I have enough to do work equals force times distance? Do I have force? Yep. Do I have distance? I do not. Okay. So remember, your whole goal, your end game is to get to here. Work equals force times distance. So let's set up Daffy T and see if we can get our distance. Okay, so it comes to a rest, so VF is 0, your time is 2, you're looking for distance, and that's all we got. Now, here's one thing is, we're talking about a wagon rolling on a flat sidewalk. What I've seen students do is once they get gravity stuck in their head, well, I'm just going to throw in negative 9.8, okay, for that acceleration. Okay, this wagon's rolling on ground. It's not falling off a cliff. It's not being thrown in the air. Okay, so gravity is not there. So this means is we do not have enough to do Daffy T. So this is about as far as these problems get. Okay, so let's go back up to this equation right here. F equals ma. Okay, do I have a force? Yeah. Do I have a mass? Yeah. So I can use that problem. So F equals ma. So negative 60 equals mass 8 times A. Okay, so what we're going to do is we're going to divide both sides by 8. And I'm going to get acceleration of negative 7.5 meters per second squared. Now I have acceleration, so now I can plug that in over here in my Daffy T. So negative 7.5. That means I did not care about VI. So I'm going to use equation number 4. D equals VFT minus 1/2 AT squared. Now the good news is since VF is 0, this whole thing goes away. Okay, so please don't write 0 times T equals T. Okay, because then you're going to have a hard time getting T by itself. Okay, so 0 times T is 0. So distance we don't know equals negative 1/2 A would be negative 7.5 times T squared. Okay, this is just the time squared. That's the only thing that's squared. And you get a distance of 15 meters. So now I have my distance. So now I can do work equals force times distance. So negative 60 times my distance of 15. and you get negative 900 joules. Okay, can work be done in different planes? Okay, so if the force is perpendicular to the displacement or direction of motion, technically we cannot calculate work. Okay, so that means if force is perpendicular to your distance or displacement, there is no work being done. Now, can you be burning energy and stuff? Yeah. Okay, but technically no work is being done. So we're going to talk about some scenarios here. Okay, so we have Bob here. He's carrying a box. Okay, he is just holding it. He's walking forward. So snapshot later in time, Bob looks the same, still carrying the box. Okay, so he didn't lift it at all. So we're not lifting it up and down right now. We're just holding the box and walking. So if you were to take a close look at that box that he's holding, he is using a force to hold that up. Okay, but the distance he is covering is this way. Okay, so if you notice that, force and distance are not in the same plane. So is Bob doing work in this case? No. So no work being done, okay, because his force is going up and his distance is going horizontal. Now, once Bob, let's say Bob picked that up from the ground. So let's take the same box before he's holding it. Let's say he picked it up, so his force is this way, and his distance would be going up as well. So his distance would be going up as well. So see how they're in the same plane? So that would definitely be work. So Bob picking up the box would be work, but once he starts carrying it and walking in a different direction, work is no longer happening. Okay, so scenario 2 is circular motion. Okay, so we're going to draw our circle. Okay, we're going to say we're spinning an object around. Okay, so force and distance. So your force, remember from circular motion, your centripetal force is always towards the center. Okay, and your distance or velocity is going to be tangent to the circle. Okay, so there's your distance or displacement. So F and D are not in the same plane, they're perpendicular. Okay, so force is perpendicular to distance, so therefore there's no work being done in circular motion. Okay, now let's talk about what if there actually kind of is some in that direction. Okay, but we'll work on that in the next video. That'll end this one.